integral. A mathematical object that can be interpreted as an area or generalization of an area. The branch of integrals is calculus. Electrical engineering uses calculus integration to determine the exact length. The purpose of the wire needed to connect is to find the space between the orange lines shaded in pink. In this case, the orange lines represent A and B. The equation has A and B above the S shape, as well as f of x and dx. Now, here's an example. Below on the graph is shown a curved line. The pink equation represents the graph. T is what we want to find out in that moment. For example, we are trying to find what liters there is in 6 minutes. We will try to find how much liters there is in 6 minutes inside the hot tub. The purple lines show where we will need to find. We will now use the equation to find out how many liters are in the hot tub in 6 minutes. We'll be plugging in 6 and 0 for A and B. Then we will put in the equation for the graph as well as dt. Now to put it into solvable form, we will have to put it into the cosine instead of the sine. Now just follow along with the equation. I think the most confusing part of this equation is when you get cosine of 1.8 and cosine of 0. Well, you see you plug in 6 for t and multiply that by 0.3 and get 1.8, and you also multiply 0.3 by 0 by plugging it in for t and getting the cosine of 0. What we find out is that the hot tub is filled at 24.5 liters after 6 minutes, or the area that is shaded green is 24.5 liters.
So, everybody knows the idea of the slope of a line. It's just the rate of change, rise over run. But in calculus, we can now think about the rapid rate of change of a curve, because curve compared to a straight line is always changing the constant rate. Which brings the purpose of derivatives. The definition of the derivative is a way to show a rate of change, but not any rate of change. It is the amount by which a function is changing at one given point. Derivatives are a fundamental part of calculus, and here's why. Knowledge bomb. The derivative of a function of a real variable, a function whose domain is real numbers, measures the sensitivity to change of the output value with respect to change in its input value, which are very complicated words. But there are many rules to solving derivatives, because there's many functions you can find derivatives for. For example, this is the power rule, and this is the example problem. What is the derivative of x to the third? And that is how you write the derivative, d over d times x. And in this power rule, you would put you put 3 in the place of n, which is a power. So the derivative times x to the power n equals n times x to the power of n minus 1. To solve this, we would plug in our number, and it would be the derivative times x to the power of 3 equals 3 times x to the power of 3 minus 1. And if you simplify that, you get 3 times x to the power of 2. Real-world applications. To find acceleration, you have to take the derivative of the velocity function with respect to time. For example, you could calculate how fast Usain Bolt would be going at an instantaneous speed. And derivatives are commonly used in biology to find the rate of muscle contraction, rate of dissolution of drugs into the bloodstream, and growth of bacteria. How did this project enhance my understanding? Why did I choose it? I wanted to figure out why finding a constant rate for an instantaneous second mattered, and it interested me in how integrals and derivatives are basically opposites of each other. My understanding of derivatives has enhanced now because I now know derivatives matter because you can describe exactly how much a function is constantly changing.